Are you ready? No.
Okay.
Let me introduce the second speaker. The second speaker is Professor Jinn Ouk Gong at the Ewha Women's University. He will give a brief talk on cosmological perturbations during inflation, classical theory, and cage issue. Okay, Jinn Ouk, please go ahead.
Yeah. Okay, thank you very much. So my presentation will be quite focused on very specific topic about cosmological perturbations during inflation. In fact, as I will tell you very soon, cosmological perturbation is not only limited to the period of inflation, but it plays a very important role, as Dr. explained nicely in the previous session. It affects basically all the observable structure. But today I would like to only concentrate on very specific period of inflation, which already Dr. explained what it is and why it is necessary. And I will tell you how we can describe the perturbations produced and evolved during inflation. So, okay. All right. Okay. So this is a schematic picture of generation and evolution of perturbations. So as you can see, on top left down, there's a quantum fluctuation during inflation, because during inflation we begin with everything begins from very, very small sub-horizon scale where quantum mechanics is dominating. So we have, due to uncertainty principle, very transient fluctuations in energy density or matter content. They are equivalent. So those transient fluctuations will disappear very soon because they are literally transient. They can only exist during some very limited time interval given by roughly the Planck constant divided by the energy scale. But during inflation, the expansion of the universe is so much faster that even if they disappear, they go outside the horizon, then they are just frozen because they are out of horizon and they cannot interact. So they are just frozen there and they become classical. Well, it has many different notions, but let me just a bit sloppy here and just keep saying about that. It becomes classical and it becomes so-called classical perturbations outside the horizon. And after inflation, because after inflation, the Hubble scale expands faster. So those modes, those fluctuation modes come inside the horizon, and then gravity does the rest thing. I mean, because there are small fluctuations, more fluctuations will gravitate stronger, and they will attract naturally more matter, and more matter piles up, then even more matter is attracted towards those places. So they become more dense and dense and dense, and eventually then those locations will exceed so-called critical density, and they will experience gravitational collapse, and they will become gravitationally bound, like galaxies, clusters of galaxies, all of the stuff. So basically, perturbations are the original, like galaxies, clusters of galaxies, and temperature fluctuations in the cosmic microwave background, and so on and so on. So what I will concentrate today and tomorrow is this part, that is very first part, such that the quantum fluctuations and the evolution of classical perturbations during inflation. Those two processes happen during inflation. So to begin with, I should say that my presentation will be a little bit boring. I will not show you as many pictures as Dakshan did. So I will just throw a huge number of mathematical equations. So I understand it will be a little bit boring. So instead of explaining in detail, this equation is what and what and what, this term is blah, blah, something like that, I just concentrate on delivering you the what it means. So I also need to follow what the flow of the content. So that's my hope. Anyway, so yeah, this is what I just cosmological perturbations, and presumably, we imagine or we expect the origin of those fluctuations during oscillation. Well, we had in the previous years for structure formation, such as cosmic strings, for example, but because of the detection of the cosmic microwave peak in the power spectrum, the cosmic strings as a major source of structure formation is now ruled out. So, precisely speaking, I should say that inflation has been testing all the observational tests until now. So there could be some mechanism, I don't know what it is, but inflation so far has survived. So that's why we think inflation is now in the part of the Cosmological model. So let me just now begin. So for definiteness, I will consider only general relativity with a minimally coupled scalar field, and the universe is described by the Friedmann-Lorentz work metric as substantial before. So now we know the background. So Sosan already explained the universe is expanding, which is characterized by the scale factor. And now we introduce small deviations from the background, both in the matrix and the matter content. Here, it will be a minimally coupled scalar field. So I mean, now the matrix is expanded in terms of otherwise homogeneous effort of the background matrix, which now you know that minus dt squared plus a squared delta ij dxi dxj for the case of flat universe, and small deviation. And likewise, the scalar field is now decomposed into the homogeneous isotropic part, so that it is only dependent on the background, on the time coordinate, and small fluctuations, delta phi, which can depend both on time and space. So this is the beginning. So first, let me consider the perturbations in the matrix. So we consider the Robert Friedmann-Lorentz work universe as a background, so that the background is given by the well-known form, and we have a small deviation. And now you can see that basically the properties of the perturbations can be classified, roughly speaking, depending on how many, what kind of indices the fluctuations are having. So, for example, we can say that it may have two time indices, right? And one time index and one spatial index, and two spatial indices. And as you can see from here, for example, as you can see, anyway, the metric has a dimension of is dimensionless. So they are just some number, but depending on what kind of query it transforms under spatial formation, we can classify them as scalar, that is on the spatial coordinate transformation. They are invariant, or they transform like a vector. So with vector, it should carry one spatial index, or rank to tensor, that is tensor with two spatial indices. So 0, component has no spatial index, so it is just a scalar. So as it as a and 0i component is contracted with one spatial index. So to form a space-time scalar, it should carry one spatial index here. So this is four-dimensional. This is a spatial vector. And likewise, for the spatial part, I can divide them into the part proportional to the background matrix, right? So basically, this describes the wiggle in the spatial cover set, and anything else that has two indices, right? So now we have a perturbations in the matrix. So now what to do is that basically what we want is to describe the dynamics of perturbation, right? And they can be described by the perturbed Einstein equation. So our first task is first, because we now have the perturbations in the matrix, our first task is to write down the part of the Einstein equation that describes geometry, including perturbations. That is, we will write first the Einstein tensor, including metrics. And one simplification here is that the simplification I will make at this point is that because we assume that the perturbations are literally, as the name stands, perturbative, very small, I will be satisfied up to the linear order in perturbation. So that means I will be concentrating on linear perturbation theory. That is the perturbation variables here, A and BI and VAPI and EIJ will only appear linear order. That is my assumption. Okay. So let me proceed. So it is just a straightforward, but a little bit tedious calculation, but it is really straightforward. So first, what you have to do is to find the inverse metric. So what I have written down here is the metric with indices down, right? So to construct the Einstein equation, we need the inverse metric, of course, which of course satisfies when it is contracted with the metric with the indices down, it should give us kilometer delta. So you can find the inverse metric perturbatively up to the any order you want. So here, let me just show you one example. So let's just find G00, right? The inverse metric of the 00 component. So I assume it has the form -1 plus some perturbation. This is because at the background level, the inverse metric of the 00 component should be -1. So because I am perturbing the metric with the indices down slightly, as you can see here, I also assume correspondingly, the inverse metric should be also perturbed slightly from the background value, that is from -1. And also likewise, I assume the 0i component of the inverse metric is of the same form. Oh, okay. This is some automatic change of stupid PowerPoint. This should be small index, small I. Anyway, so if I contract the 00 component, right? So I just plug a mu and mu to be 0, then it should be just 1. So I just sum over the 4 indices over mu. So I sum over 00 and I. Then I have this result. Okay, so this is the G00 component I assumed, and this is what to be determined, the inverse metric of 00 component. So alpha should be determined. This is coming from contract of 0i component. So I told you only up to linear order in perturbation. So you can see that this is the two perturbations. Beta is just a small perturbation. So I just drop down. And also here, you can see that there should be the product of two perturbation variables, alpha and A, which I just drop. So once I at linear level in perturbation theory, then this is what we have. And we want this to be the same as 1. So this combination, 2A minus alpha, should cancel each other. So that means this unknown alpha is 2 times A, right? So this is a very straightforward way of fixing the inverse metric perturbations, and you can just do the rest exactly the same way. So anyway, we just truncate a linear order. They have already extracted the indices of the spatial vector and spatial tensor are raised and lowered by the background conformal metric that is just a simple delta ij, right? So because now we have the inverse metric, it is just a straightforward but a little bit tedious job to calculate the Einstein tensor. So here's the result. All right. So we have quite complicated combinations of the perturbation variables. As you can see, phi is here, B is here, Eij is here. A is here, etc. And just one thing is that here, capital delta means spatial Laplacian. So two derivatives of the spatial coordinate. Okay, and of course, if you have any questions, please stop it at any time. Anyway, up to here, everything is just a straightforward calculation. So there should be no confusion, I hope. Now, we just go one step further. That is, we can now decompose the perturbations into the pure scalar and transverse vector and transverse traceless tensor component. That is, the zero I component perturbation, curly bi, because it carries one spatial index, it can be decomposed into the gradient of some scalar plus pure tensor. And likewise, the spatial component, some part of the spatial perturbation, Eij, carries two spatial indices. It can be written as a gradient of a pure scalar and gradient of pure tensor. Of course, the indices interchanges because we want the symmetry of the indices and pure tensor. So pure vector and pure tensor means the vectors are traceless, transverse, and the scalar and the tensor is traceless and transverse, right? So we have now pure scalar perturbations and pure vector perturbations and pure tensor perturbations. So once we have decomposed the zero I component and Ij component of the Einstein equation of the vector perturbations, we can just simply plug them into these expressions, Bi and Eij. We just expand them in terms of pure scalar, vector, and tensor, and we arrange them. Then what we have is, before that, let me just talk about how many variables we will have. So for scalar, we have four scalar functions. So let me just go back a little bit. So we have four scalar functions. So A, right? And Wi-Fi, these two are obvious. And now we have one scalar gradient from here and another scalar gradient from here. So we have 1, 2, 3, 4. We have now 4 scalar degrees of freedom. Okay. For vector, there are two vectors, Si and Fi. So because they are spatial vector, they have 3 components each. X component, Y component, and Z component, right? But we need not specify all these 6 components because it is under the transverse condition. So because of thanks to the transverse condition, we can remove 1 degree of freedom from each vector. So we can eliminate, we can write one component in terms of the other by using the transverse condition, and it can eliminate 1 degree of freedom. So for vector, we can remove 1 degree of freedom each. So we have 2 components in each vector. So that means for vector perturbation, we have total 4 degrees of freedom. And likewise for tensor, because we have 3 dimensions, tensor can be described by 3 by 3 matrix. We of course are symmetric matrix because it should be symmetric under the exchange of the spatial indices. So the symmetric 3 by 3 matrix has 6 independent components, right? So it's the upper triangle or lower triangle, including the diagonal components. We have 6 components. But we have the traceless condition from which we can remove 1 degree of freedom, and the transverse condition because we now have 1 more indices compared to the vector case. We can remove 3 components. So we can remove 1 component and 3 components. So that means we can remove up to 4 components. So out of 6, we can remove 4 by using the transverse and traceless conditions. And now we have only 2 degrees of freedom left in the tensor. So the total number of degrees of freedom we have to solve are 4 from scalar and 4 from vector and 2 from tensor. So there are in total 10 degrees of freedom. So this is, let me just comment that this is consistent with the fact that the 4 by 4 symmetric matrix, the matrix have 10 independent components. Okay. So now once we have extracted out how many degrees of freedom we have to solve, this will be important later. Now we can just plug back these decompositions into the perturbed Einstein equation, and we just arrange a little bit. So here it will be convenient to have one index up. So here I am writing all 2 indices down, but practically it is more convenient to raise one index up. So I will be writing G delta G 1 0 up, 1 0 down. Likewise, delta G 1 index 0 up, down I, or the other way around, up I and down 0. And likewise, finally, delta G up I and down J. And also here, because I am considering the spatial part, it is very convenient to decompose the pure spatial part into the trace part, that is I and J the same, and the trace part, that is, if I put I and J the same, it vanishes automatically. So you can do this very easily, and here are the results, right? So the third equation here is the trace component, as you can see, I, and this is traceless component. You can easily see from here that if you put I and J the same, it automatically vanishes. Okay, so this is the geometric part. It's very, very straightforward, but it's a little bit tedious. But I believe you will have no problem in understanding this part. It's just nothing but really straightforward calculation. So any questions up to this point? All right. So because we are trying to write down the Einstein equation, now what we have done
Jinn
is
Ouk, a very simple question. So far your decomposition of the 10 components in terms of the massless particles little group rather than massive degrees, because you are separating out the so for the vector rather than 3, it's I mean the gradient things, and also the transverse part, right? Longitudinal and the transverse part. So it seems that everything is already you have in mind in terms of the massless degrees freedom, right? So my question is
here yes.
So little group is rather than SO3 is seems to be how does it call E 2,1 or something.
Okay.
But if we add also the matter field and let it be coupled with a metric, and if some of the metals are massive, then whether this kind of decomposition still holds, or at that time there is a kind of mixing occurs.
Okay, that's a very interesting point. So first of all, here I am not talking anything about meta sector. So this up to this part, it should preserve all the symmetries of the original system. For example, if I am talking about the space, it will preserve the symmetry. What was that? SO 4,1 or something like that. I just forget. But if we introduce meta sector, and of course it couples to gravity, then it will break some of the symmetry. So I mean, for example, it will be breaking the diasymmetry, for example, and of course it introduces very rich structure. So basically, yes, you are right. If we introduce some meta sector, then unless we impose some special conditions on what properties the meta sector has, it will break in general the symmetries of the geometric part. And
okay, thank you.
All right, and that is a very interesting point, but that's a little bit out of my streamline. So let me just skip that part, although that's a very interesting point. Anyway, so all right, so up to now we have done what we have done is the left-hand side of the Einstein equation, that is the geometric part. So we have the rest half, that is the right-hand side, the energy momentum tensor. And fortunately, it is much easier than the geometric part. So we just consider minimally coupled scalar field so that the kinetic term is just minimal and we have the potential. So the energy moment tensor is following the standard way. That is, we just perturb the Lagrangian with respect to matrix, and that gives us the energy moment tensor, which is given by very straightforward form. So now we have the scalar field, which we can divide, we can decompose into the background phi 0 and fluctuation theta phi. And we also have metric. So we should also include the metric fluctuations here, right? So we include those perturbations and we expand everything, and we are keeping up to linear order. It's very straightforward. A little bit tedious though, but it's much easier than Einstein tensor. Then these are the results you will have. So we have a 0, component, 0i component, II component, and a trace II component, and trace list ij component. Okay? So fine. Up to here, everything is just a straightforward calculation, and you should have no problem. So because now we have the left-hand side of the Einstein equation and right-hand side of the Einstein equation, so now we can match them all together. So we match 0, component, 0i component, trace ij component, and trace list ij component. Then here are the results. And what is very nice to hear is that at the level of linear perturbation theory, scalar, vector, and tensor do not talk to each other. As you can see, we have the trace equation, vector equation, scalar equation, and vector tensor equation all separate. So the vector, for example, vector does not affect the evolution of a scalar, and scalar does not affect the evolution of a tensor, something like that, at the level of linear perturbation theory. So they are all decoupled. So this is so-called decomposition theory. All right. So these are the equations we will be playing with. So any questions up to now? So again, it's
So the Jinn Ouk, you mentioned that there were, for example, 4 scalars, right? Could you remind me the symbol that you wrote for the 4 scalars?
Okay, so the 4 scalars I am using are A, this is the 0, component of the
Right.
perturbation, and phi, this is the
Good.
let me roughly say trace part of the spatial perturbation.
Yes.
And I have B, that is 0i component, and E, this is ij component.
Okay. So
And
out of
likewise,
those,
for vector, I have 2 S and F and 1 tensor Hij.
okay. So out of those 4 scalars, which one are coupling with the phi field and which one are not coupling?
As you see, for example, A is coupled, right? As you can see, A is basically. So in fact, that's why this is something I can tell you a little bit later. This is why sometimes it is called, it can be identified under some special gauge conditions, which also I will explain you later, gravitational potential, because it couples to matter.
And I do not see capital E. Are they also coupling here? Oh, I see. It's all mixed.
Yeah, it's all mixed. It looks quite complicated equation.
So it's really, so before it was, the 4 independent scalars decoupled, but now once you introduce phi, it becomes 4x4 matrix all coupled, right?
Well, exactly speaking, what I mean decouple is that, what should I say? Yeah, decouple, I mean scalar, vector, and tensor do not talk to each other.
Right.
That is what I mean decouple. But scalars are all tensor separate. So you see, within the same kind of perturbations, they are all mixed up.
Okay. What was capital H?
Oh, sorry, capital H is the Hubble parameter.
Hubble parameter. Okay.
Yeah. A over A dot over A, of course. And V prime here is the derivative of the potential with respect to scalar field.
And
well, finally, the over dot means a derivative with respect to a constant time t.
So all these are in the first order in perturbation, or second, I guess first order, right?
Everything up to first order in perturbation. So I am also keeping both delta phi and delta phi here, the scalar field fluctuation.
Good. Okay, thank you.
All right. So any other questions? Okay. So I believe up to here it's everything is straightforward, and you will find no problem in checking yourself. So let me just proceed. So as I told you, one important thing is that scalar, vector, tensor, they are all decoupled, so they don't see each other. And you can see that if we see the scalar equations, this one, right, this one, they have on the right-hand side the scalar field content. So I can say that scalar field stores the scalar perturbation in the matrix. Meanwhile, vector and tensor have no source. The right-hand side of the Einstein equation, that is the energy momentum tensor part, are zero. So they are unsourced. So unless there is some special kind of source, like a vector field, they don't have a source. Okay. So, and finally, because I am taking no anisotropic tensor, that's some very special kind of a vector content. So that affects the tensor perturbation. So tensor perturbation can be sourced by the anisotropic stress, but it has no stress, so it's just the right-hand side is just zero. So tensor equation is also not sourced. All right. So
I have a question.
Yes.
Hi, Jinn Ouk. So at second order in the perturbations, then there will be mix between everything.
There are mixing, but I am not considering second order perturbation.
I'm just going to ask, then the tensors will be sourced by...
It is a source. It is a source. Yes, indeed.
Yeah. Okay, thank you.
That's a matter of fact. So if we extend up second order, then they are normal totally, but everything is source. All right. So vector is a source, tensor is a source, and also scalar is additionally source. All right. So far, so good. But now we just go back a little bit and talk more exactly about perturbations and background. So we can easily say perturbation, but perturbation means there is something we can identify as a background, right? If there is no background, we cannot say if something is perturbation or not, right? But the problem is that because general relativity grants us the freedom to choose whatever coordinate system we want to use, right? So this is one very basic aspect of general relativity. It grants us the coordinate freedom, right? So that's why everything in GR can be formulated in a covariant way. But the problem is that because we have the freedom for coordinates, it is very ambiguous to identify which coordinates we can use to describe the perturbation. That means, okay, we have some quantity and we can identify associated with that specific point what is the fictitious background. The background can be different. So roughly, for example, we have, say, two perturbations or two observable quantities, A and B, and we may choose one coordinated system such a way that A vanishes, but B is not in the background. Or we can do the other way around. So just to say perturbations are such and such is not enough, but we also have to specify what is the coordinate system we are using to describe the perturbation. So let me just tell you the scalar perturbation in more detail. Say that we have a scalar quantity, hat phi, at some specific point P in the real perturbed universe, hat U. So perturbation becomes meaningful only if we can identify the background value, phi 0, associated with the point P. So what's that? That's the question. So to specify the background value, we have to specify what is the corresponding background point associated with P that maps P point in the real universe hat U to the fictitious unperturbed background universe U. So this is what coordinate system does, right? So we need some kind of mapping that maps P into the corresponding point X mu. Only then we can write perturbation delta phi as the difference between the real at the space-time point P and X mu, which is the map of P in the unperturbed universe, right? But there's no natural choice of the coordinate system. We can just adopt whatever coordinate system we want. So we can, for example, make use of, very easily speaking, we can make use of the Cartesian coordinate system to describe three-dimensional space, or we can use spherical coordinate system. And well, one is as good as or as bad as the other. There's no a priori reason why one coordinate system, say Cartesian coordinate system, is superior than spherical coordinate system. So it depends on which kind of situation we want to describe. Say that if we want to describe some spherical system, symmetric system, then absolutely spherical coordinate is superior than Cartesian coordinate system. But it depends on situation. It depends case by case. There is no a priori better coordinate. So we have to control what is the mapping between one coordinate to another coordinate. And now here is the important point. So what we do in that change is just to change the coordinate system. We change from Cartesian coordinates to spherical coordinates, right? And any change induced by changing the coordinate system is not physical. It's just because we are using different measure or gauge to describe the same thing, right? So we can describe sphere in the spherical coordinate system, that is, R is just some constant, right? And it can be mapped into the Cartesian coordinate system such that x squared plus y squared plus z squared square root is some constant. But they do not mean different things. They are meaning the same thing. But simply how they appear in the coordinates is different. So this non-physical change is called gauge transformation. Simply the change in the coordinates. So let me just tell you a little bit more specific. So let's suppose two different coordinate systems, x mu and x hat mu, and which map the same point P here into different points, x mu and x hat mu, right? And these 2 points are related by space-time vector psi mu, right? Then if the transformation is infinitesimal, then the perturbation we can see by using the head coordinate system is, of course, the background value minus, the real physical value minus the background value associated with this head coordinate system, right? And this real physical value can be written in terms of unhead coordinate system, the background value by using the unhead coordinate plus the corresponding fluctuation, right? So we plug it here and we arrange a little bit, then this is the fluctuation in the scalar quantity in the unhead coordinate minus the difference, minus the difference in the head and unhead map. And we just Taylor expand by using the fact that the head coordinate is different from the unhead coordinate by this infinitesimal factor, and we just Taylor expand, right? Then this is what we have. And because the background is homogeneous and isotropic, this phi 0 only depends on the time. So we just choose mu to be 0. Otherwise, it will just disappear. So we just keep only 0 components, and this is up to linear order in gauge transformation, how the fluctuation will look different in one coordinate system, that is x coordinate system and x head coordinate system. So this is just the repetition of what I just told you. The notion of perturbation becomes different by adopting different coordinate system because the corresponding background value becomes different. Okay, so this is the essence of gauge transformation. Because we can use different coordinate system, there is freedom. Also, there is freedom in fluctuation. So we have to specify how the fluctuation in one coordinate system looks in another coordinate system. That is what is meant by gauge transformation. Okay. So any questions here?
So, Jinn Ouk, so far what you mentioned is the general coordinate transformation, right?
Yeah.
But
exactly.
if we get to the vectors and the tensors as a massless equation of motion, they have a different kind of gauge symmetry, right?
This has nothing to do with equation or whatever. It is just a coordinate transformation, nothing.
At this level, okay.
Yes.
Okay.
It's just a kinematic description. There is no dynamic. Okay.
Okay.
Very good. So any other questions? Okay. So let me just now be a little bit more specific to the case of our interest. So exactly speaking, mathematically, gauge transformation of a generic tensor quantity is given by the exponential map of the Lie derivative along the transformation vector. But regarding the metric perturbation, there is a simpler way by demanding that the line element ds squared should remain invariant on the gauge transformation. Even if we just use different coordinate system, the space-time interval should remain the same. So let's assume that the time coordinates and spatial coordinates are transformed slightly infinitesimally by these two vectors, psi 0 and psi I, then corresponding change in the scale factor and the new time coordinates and new line and new spatial coordinates are very straightforward. This is just nothing but just a Taylor expansion and taking derivatives. Okay, and now we demand the line element should be the same. D as a head square, that is the line element described by using the head coordinate system should be the same as the line element described by unhappy coordinate system. So we can map one by one how each should be the same. So for example, if I compare dt square part, the 0, 0 component, 2 times a hat plus psi 0 dot should be the same as just the 2a. So demanding these two the same, I can see that how the metric perturbation in one coordinate system, hat coordinate system, can be written in terms of unhat coordinate system. So this psi vectors describe how those two coordinate systems are translated. In time, it should be translated by x psi 0, and in space, it should be translated by I. Right? You can straightforwardly find on the coordinate transformation the spatial transformation vector in terms of gradient of some scalar and transverse vector, right? And you can decompose also the 0i component of the metric perturbation and ij component of the metric perturbation in terms of a scalar vector tensor, and it is just straightforward, right?
So
one thing I
Jinn
have-
Ouk, the psi that gauge degree freedom, doesn't it affect the homogeneity and isotropy of the background?
No. It is just only a matter of perturbation. So
But psi is a function of space also.
the transformation, as you can see, all something. Sorry? Say again, please. Say again, please. Hello?
Hello?
Yes. Please say again.
Yeah, so my question is, for example, specifically psi 0, if it is of not only function of time, but also x, as you wrote here, the space x, then whether it will destroy the homogeneity or isotropy of the background.
It does not. No, it does.
Doesn't?
No, it does not.
Why not?
It doesn't. Because it has purely affecting the perturbation. So you can see here, the whole point is describing the perturbation. So all appeared here are perturbation variables, basically. So how the perturbation A in coordinate system is written in terms of the same perturbation in unhat coordinate system. So, all right, here. So, all right. So the change here is just given by some transformation factor, right? So probably you may wonder because this U right side here is unperturbed universe, but this is time dependent quantity. So isn't it destroying the homogeneity and isotropy of the background? Probably that is the question, right? I think.
Okay.
But it does not because what we are worrying is basically the mapping of the perturbed universe into the background universe, right? So it is not simply the transformation in the background universe. So regarding the background universe, if we forget about perturbation, then there's no difference in x system, x coordinate. Perturbation can map is regarding the transformation of the perturbation. So that's why it should depend on space and time. because the coordinate transformation can mix space and time altogether.
Okay.
So is it the answer for you?
Yes, I have to think about a little bit more, but I understood what you're saying, yes.
Okay, so all right. So here's just one comment I want to make. So you can see that also in the previous page, many metric perturbation variables are depending on the translation vector, could be 0 or but you can see that, for example, pure tensor perturbation remains the same. I mean, whatever coordinate system we use, they are the same thing. And likewise, this specific combination, the vector S minus A times F dot also remains the same. So you can see that they just cancel each other, right? By multiplying A here and taking time derivative and multiplying by A. So they are the same, whatever coordinate system or gauge we use. So these such variables are called gauge invariant. Literally, as it means, whatever coordinate system we are using, the value of these variables are the same. All right. So, all right, let me just skip this part. So, very good. So, tensor perturbation is fortunately gauge invariant, and vector perturbation seems gauge dependent, but if you go a little bit back and have a look at the perturbation equation, you can see that all the vectors appearing in the equation are the specific combination of SI minus ASI dot, right? SI minus AF dot. And as I told you, so whatever coordinate system, they are the same. So we don't have to worry about that. So the only question is the scalar perturbation, because the scalar
I'm sorry, Jinn Ouk, I cannot hear you. Jinn Ouk, can you hear me? I think that Jinn Ouk has some
Hello?
problems connecting. Yeah, hello.
Hello.
Yeah,
Sorry,
yeah. Can you hear me? I'm sorry. I cannot hear you. Jinn Ouk, can you hear me?
Hello.
Yeah, hello. Yeah.
All right. I am very sorry. The connection is a little bit problematic. Yeah. So okay. So now can you see the screen again? Can you see the screen again?
Yeah, I can see.
Okay. So although this still is working, so I have no idea when I will be offline again. So let me just anyway proceed until I am kicked out. So and probably I have to finish in a few minutes, right? It's already 12. All right. So let me just go a little bit quickly. So there are two different ways to deal with the gauge issue. So one is just a fixed gauge, and we just work in that fixed gauge. So say that we work in the gauge such a way that the fluctuation in the scalar field vanishes. So then we demand the scalar field delta phi is vanishing, and it can be written in terms of the generic perturbation, the necessary time translation from a generic hypersurface with constant time to a new hypersurface where the scalar field vanishes is given by this amount, right? So this I can put the subscript delta phi, meaning that this is the amount of time translation where delta phi vanishes, right? So this is one strategy, and in fact, it is very straightforward. We just fix a specific gauge, and we just work there. This is one specific strategy, and the other strategy is we use a special combination of perturbation variables in such a way that it remains gauge independent. Whatever coordinate system we use, it remains the same value. For example, consider this specific combination. Phi phi, roughly speaking, the trace part of the spatial matrix minus this specific combination. Delta phi times h divided by phi 0 dot. And this quantity is gauge invariant, as you can see very easily. So this is one specific combination of the gauge invariant variable. And of course, this is not the only gauge invariant scalar perturbation variable, but you can construct hundreds or thousands of different combinations of the gauge invariant variable as you like. So other famous gauge invariant variables, the so-called bottom potential or the uniform density hypersurface curvature perturbation, usually denoted by zeta or whatever. There are many different variables. So there should be some specific reason why we choose one specific gauge invariant variable. There should be not only just simply because it is gauge invariant. There should be some good reason, and I will tell you a little bit later why I will be sticking to use this specific combination. Anyway, this is the meaning of this variable curly r is very straightforward. It is simply the curvature perturbation evaluated on the hypersurface where delta phi is 0. You remember that this combination is the amount of time translation from a generic hypersurface to the hypersurface where delta phi vanishes, right? So in that sense, this curly r is basically the curvature perturbation where delta phi is vanishing. And for the case of scalar field dominated universe, in that case, if delta phi is 0, the I0 component of the energy momentum tends to vanish. That is, there's no momentum flux. And it's something like we are following the scalar field and observe what's happening. So because we are moving together with the scalar field, we do not see momentum flow. And we are moving together, so we can say that we are moving together. So this gauge is called co-moving gauge, and correspondingly, this variable is the curvature perturbation evaluated on the co-moving hypersurface, or shortly, co-moving curvature perturbation. And of course, it can be evaluated on any hypersurface because it is gauge invariant. Anyway, so because I will be talking about the co-moving hypersurface, the co-moving curvature perturbation, our next task is what is the master equation, the governing dynamical equation of the co-moving curvature perturbation. So I will be telling you 3 different ways, but I think I have no time, so I just skip one way, but I just move directly to the second way. So The second way is we just work in the co-moving gauge from the beginning and we find the equation of motion. So these are the Einstein equations, the 0, component of the Einstein equation, and 0I component Einstein equation, and traceless ij component Einstein equation. The trace ij component identically identical. So what you can see is that, okay, so here are two perturbation variables other than curly R, which is the variable we want to find the equation of motion. So that is A, the 0, metric perturbation, and B, 0I metric perturbation. And as you can see from these first two equations, we can solve for A and B without solving for A and B. I mean, you can see that here A and B are not dynamical in the sense that there's no time derivative here. So we can just algebraically rearrange these equations and we can write A and B in terms of curly R, like this. And it is not mere coincidence that 0, and 0I components can be algebraically solved. This is not mere coincidence, but I will relegate the why it is so in the next approach. Anyway, plugging these relations A and B in terms of curly R into the remaining one equation here, and we rearrange, then we obtain the equation of motion of common curvature perturbation. This is the master equation we will solve, and the final approach, the third approach, the first one I did not explain because I'm running out of time, is more closely related to the quantum theory of cosmological perturbations. That is, we will be working with the perturbation action and we will derive the corresponding equation of motion. And I will explain it tomorrow when I am talking about the quantum theory. So I will just stop my presentation today here, and thank you for listening.
Okay, thank you for giving the nice review talk on the cosmological perturbation during inflation, the part 1. Okay, that's so. Any questions or comments?
Yes.
Okay, yeah, yes, yeah.
Jinn Ouk, you just said that because 0, and 0I components, the perturbation variables are essentially don't have time derivatives, you can solve easily algebraically to find for them.
Yes.
What happens in more complicated situations where they might have derivatives? Can you still do that?
What?
In more complicated cases,
yes,
where
more complicated equation, what?
Where A or B might have a derivative of time or something, then can you still do this?
Well, probably if you are thinking of more complicated theory of gravity, it may happen. But in the context of general relativity, it does not happen. It does not happen. 0, and 0I components of the Einstein equation are always of this form. So that will be explained tomorrow. So
even in multi-field theories?
No, it does not. It does not matter. These are only geometric parts. It doesn't depend on what's happening in the matter part.
Right. Okay. Thank you.
So this is a purely geometric part. So if we want to introduce some dynamics here, then you have to go beyond the GR. At the level of GR, this is just the case. I will explain you tomorrow. Why
I see. Okay. Yeah, I was talking about something a bit beyond. Yeah, where you can get then time derivatives, and then it's
that's different. That's different.
Can you still solve it this way though, or is
Well, then of course we cannot do that way, because in that case, if A and or B has time derivatives, then they are dynamical variable, and you have to solve for them.
I see. So it's okay. You still solve, but it's just more complicated. If you
It's much more complicated.
okay, RIP. Thank you.
Jinn Ouk, may I see your master equation for scalar?
Yes. So basically,
This
is the master.
So this is the equation for the scalars in some gauge invariant way or something.
Yeah.
So originally there were four scalars. Every scalars are following this type of equation, or?
No. Only this type of this perturbation variable curly R follow this equation. If you use different variable, then of course their equation of motion is different.
I see. This is only for curly phi.
Curly R, yes, only for curly R.
Oh, curly R. Okay, good. Okay, thanks.
Any further question or comments? Okay. No, then let's thank speaker again and thank you